Okay. Hello, everyone. Can everyone hear me okay? Okay, good. So, welcome to the third concurrency lecture in this course. Let me just enable the screen share. 1 second. Okay. And I have to, yeah, okay. Here we go. Good. So, no, wait. Yeah. So I wanted to do this. So let's stop. Okay. Good. So I'm not sure what's the shared screen. I just wanted to start with some news. So today was released a new initiative for privacy preserving proximity tracing. It's a pan-European initiative that is meant to contain the coronavirus once the current lockdown phase is finished. And EPFL had an important role to play with it. So the screen that you hopefully see, I don't know, do you see this privacy preserving proximity tracing screen now, or the other one on asynchronous programming? I have a problem with seeing that. Okay. Okay, so it seems you see the screen here. Good. So the idea is that that there will be a open source platform so that people can be notified when somebody in their proximity fell ill with the coronavirus. So the way it works is it uses Bluetooth to record proximity of other mobile phones, and everything is randomized, so you won't get clear names, you will just see random IDs. If somebody gets diagnosed to be positive, then essentially the people that were in contact with that person get a notification that they were in proximity of essentially somebody who was infected, and that they should let themselves test and isolate and things like that. So I believe that's is the first way to actually do the second phase after the current lockdown, to have essentially the testing and tracing that can do that while being fully privacy preserving. So I find that quite an important milestone, and I just hope that it will receive the widespread adoption in Europe. So I don't know, maybe you've come across it in the press already. The nice thing is that a lot of EPFL researchers and professors were very closely involved in developing this in working together with other institutions, the ETH Zurich, the Fraunhofer Institute in Germany, Robert Koch Institute in Germany, and so on. So there's a broad initiative of over 100 scientists that actually developed that, and hopefully we will that will be able to provide a way out of this current lockdown, which is pretty severe, and I'm sure is weighs on all our nerves a little bit. Okay, so in fact, after that start, let me just go back and share the other screen. Okay. After that start, the topic of this lecture is actually not a little bit connected, so this is nice. It's about asynchronous programming, and asynchronous programming is something that you need to have under your belt if you want to do mobile apps and server apps for mobile apps, because essentially asynchronous programming is about bridging the gaps where you wait for something to happen that will take some time because, well, the message hasn't been sent yet, or it takes some computation time, or it's on a different device that computes it in its own schedule. So it's basically about waiting. And a good way to demonstrate this is in this slide here, where we have our virtual coffee shop. And here we have a very inefficient coffee shop first. So there are clients, client one, so sorry, client two, no, okay, now client two and client one, and they want some coffee, and the first client goes into the shop and says, I'll have an espresso. The coffee shop has a seller, a person at the cash register, and a person that makes the coffee. So the seller would essentially take the order and tell the coffee maker to make an espresso. The coffee maker makes the espresso. So there is the coffee maker. It gives the espresso to the coffee seller. The coffee seller passes the coffee back to the client. At the same time, client two is in the shop, and but they have to wait, according to this diagram, until the first client is served. And then the client two can say, I'll have a ristretto, and the whole thing happens again. So essentially, from seller, it goes to the maker goes back to the seller, and the seller goes back to the client. So what you see here is a lot of inefficiency. Everybody is waiting. The clients wait for their coffee. The client two has to wait a long time because the client one has to essentially be served completely until the client two can place an order. And also the coffee seller is inactive most of the time. So essentially its periods of activity are here and here and here and here. And here it's waiting, and here it's waiting as well, and waiting essentially while the client is also waiting. So in this system, which is essentially the traditional synchronous system, lots of people are waiting. So we might say, okay, maybe we can solve the situation a little bit by adding more resources, adding parallelism. So we can try that, and that would give us to this picture here, where we see, well, if our clients are waiting too long, then let's just double the personnel, have 2 coffee sellers and 2 coffee waiters. And now it goes indeed faster. The first client goes to the first seller. Oh, sorry. Yep. Goes to the first seller makes the coffee, and it goes back, and the second client, when it comes in, it can immediately place the order to the second seller and get its coffee. So clients don't wait anymore, but for the sellers and the makers, it's actually worse than before. They're even less employed than before, because now each seller has essentially only 2 short periods while they take the order and while they deliver it, and each maker makes only 1 coffee, even though the maker would have the time to make 2 coffees. So that image is a little bit the image of traditional synchronous computing. You can say every arrow that goes here is really a procedure call, and then that procedure call or method call, and then that method calls another method, and each method has to wait until the called method returns with a result, and then it can continue and return a result in turn, and that's how the whole system works. But we'll see that we see at this example that it's very, very inefficient. Most of the participants end up waiting most of the time. So what would be an ideal system? What would be a better system that probably coffee shops have implemented all over the world, because they're not programs, so yes, they have some natural smartness. So of course, what happens is if you have this role between a seller and a maker like that, well, I guess in most coffee shops, they would actually have a pipeline, but let's not talk about that. So let's say if they have a seller and a maker like that, so what you could do is the client could come and say, I'll have an espresso to the seller. The seller tells the maker, and then the seller turns around and takes the order of the next client here, while the maker makes the coffee. And that way the coffee seller can essentially store the order, queue the order. When the coffee maker says, well, I'm done with the espresso, then the seller can say, well, yes, okay, and now please immediately make a ristretto. And that's what would happen here at this example. And then it's done again. So that way, everybody is better utilized. You see that the coffee seller here is busy more of the time, and also the coffee maker is busy, but the clients have to wait less. They have to wait a little bit more than in the previous scenario, where essentially every client had a seller and a maker to serve it, because the bottleneck here is the maker, right? So you see the maker has to get around essentially to make one coffee after another. So we could refine the systems maybe by just adding 2 coffee makers, and then it would go faster. But the point is that essentially, given the resources that we have, we get much better resource utilization. That means everybody is busy more often of the time. Okay, so humans can do that. What would it take to have programs do that? Because we see the critical thing, of course, is here. So essentially this context switch. So between here and here and here and here, the seller has to essentially serve different clients and essentially remember the state of things for different clients. So let's see what we need to do to put this in a program. Sorry, we have one more. Yeah, the previous example where I said, well, the maker is still the bottleneck. We actually do have an example how to make that better. So in this example here, now you see 2 makers, and that's essentially the case where the clients are served just as fast as with the previous system, but we save on 1 coffee seller. So here you see we have the client 1, it proceeds as before, but now it's the first coffee maker that makes it. Yeah, like that. And we have the second client, that essentially, as soon as it comes in, it orders the ristretto, the coffee seller is free to serve it. It goes to the second coffee maker, it comes back. So in this case here, you see we have a service which is just as good as with the essentially 2 coffee seller, 2 coffee maker examples, but now we have essentially economized on a coffee seller. We only need 1 of them. Good. So what does it take to put that into programs, this sort of asynchronous execution? So asynchronous execution means we have an execution, a part of our computation happens on other computing units. And furthermore, when that happens, then essentially the person who essentially commanded that work shouldn't have to wait for the termination. Essentially, the person that issued the command should be able to do other things until that work is finished. And the goal of that and the effect of that is better resource efficiency. Okay, so before we go back to the coffee shop, let's do a simpler thing, coffee break. So we have a program coffee break, and it consists of the following steps. So we need to make some coffee, and then when the coffee is made, we want to drink some coffee, and we also want to chat with the colleagues. And the way that's written here, it's strictly sequential. So essentially we come in, we make the coffee. As long as the coffee is made, everybody's silent. Then once the coffee is done, we drink the coffee and we chat with the colleagues. So what can we do to make this essentially more interactive? So the idea is that the make coffee, here you saw that the previous one, essentially it's a method that takes unit and returns a coffee when it's done. And the new formulation of it would be to say, well, if the make coffee still makes a coffee, and when that coffee is done, it invokes a function called here coffee done, this one here. And the coffee done function takes the coffee and just essentially does nothing in particular. It will drink the coffee, which is a side effect. So it takes a coffee and returns a unit. So that thing, this thing that essentially takes something and then just uses it and returns unit, that's often called a continuation. Oops, sorry. No, went back. A continuation, which is essentially the computation that happens when something is finished. So in this case, our continuation is the thing that happens when the coffee is made in this line, and then we call coffee done with the coffee. So if we organize things that way, we could write our coffee break like this. We could say, okay, make coffee, and now we have to tell the make coffee what should happen when the coffee is done. So what should happen is, of course, we want to drink the coffee. And then we have chat with colleagues. At this point here, we have still a strictly sequential system, but we could now make it parallel. So we could, for instance, here have a fork, write a fork around the whole thing. And now we would have essentially one parallel thread that makes the coffee and drinks the coffee when it's made. And during the whole time, we could chat with our colleagues. So that's essentially an advantage here that we have in this system. Good. So what has happened here? We went from the make coffee before to this new version that had the callback. Can we generalize that? So what we can do is that we can say, given a program like this, so it's a program that takes some input of type A and some output of type B. So that's a synchronous program. We call it with the A, we wait until the result is there, we continue with the B. To turn that into an asynchronous program, what we change is the type signature. We say the new program essentially still gets the input A, but it takes another input, which is the continuation. So that's essentially a computation that once there is a B, can continue and finally return with unit, or essentially return with unit means it just computes and that return is the end of the program. Okay, and then the program itself has also type unit because the program doesn't return any useful value anymore. That's again the end of the whole computation. What the program here does is simply it takes this intermediate result A, and once it has transformed it into a B by its own computation, it invokes the continuation here. Okay, so that's essentially the idea that we go from programs with parameters A to B to programs which take the same input and another continuation, which has the type B to unit, and the return type of the program is unit. That's a completely systematic thing. You can do that everywhere and turn essentially the whole computation into something that can be asynchronous. Okay, so once you have asynchronous programs, how do you make bigger ones? How do you combine them? We know how to combine normal programs. We just take the results and pipe them into the inputs of further functions. That's just function composition. What does that look like with asynchronous programs? So let's see. Let's say we have this make coffee as before, you see here. Same signature as before. And now we want to use that module, that component, to write a function that makes two coffees. So its continuation says, well, I want two coffees here and here, and I return unit. So how do we get from one to the other? How can we use the make coffee routine to make two coffees? So here's how we could do that. Let's see. So what we want to do is, so make coffee is essentially a thing that we now imagine sort of runs in parallel, that there is some parallel things. I have abstracted over that a little bit. So let's say make coffee. It's a black box. It does something in parallel. Once it's done, it essentially invokes that thing. So to make two coffees, we invoke it twice. We make a coffee here and we make a coffee here. And because of the parallelisms, we assume that these things are essentially not sequential. We don't have to wait for the first one to finish before we run the second one, because the actual work, make coffee, essentially returns immediately. It just runs performs this computation in parallel. Okay. So we have two coffees, we call two coffees, but what do we do with that now? So let's see, what do we have to do is we have to essentially work on this continuation K that we pass into the two make coffees. And the problem is that because they are parallel, we do not know which one will return first. One of them will return first. So we have to keep track of essentially what results we're getting. So the way we do that is that we have a variable, a mutable state here called first coffee, which is essentially the first coffee that we got from either one of those two make coffees. And its type is option coffees, and its initial value is none. So when we essentially get a coffee, so the continuation K gets invoked from either one of these two make coffee methods, then what we do is, so we get the coffee, we ask the first coffee variable, is the first coffee none, which means that it's the first coffee that we're getting. So we set that. The first coffee now is sum of coffee. So we set the first coffee. On the other hand, if we already got a coffee in first coffee, so it's some coffee too, then we know that essentially we have now both coffees, and we can run our own continuation coffees done with the two coffees that we have. One coffee is the coffee that we just got from the second continuation, and the other coffee is the coffee that we stored in the first coffee variable. Pooh, that was quite hard. So it seems asynchronicity is hard. Once these events can happen in any order, you have to do quite a lot to essentially get everything synchronized and lined up again. And it seems for these sort of things, you have to add quite a lot of mutable state to keep track of things, which is not so nice. Good. So let's continue this a little bit. So let's say, what if another program depends on the coffee break to be done? So we have this coffee break thing. And then essentially once the coffee break is done, if everything should be asynchronous, we have to make that take a callback too. So that would work like this one here. That we say, okay, so we have a coffee break. And it says, well, here's my continuation. When the break is done, the break doesn't produce anything directly. So its output, so to speak, is unit. So break done is just a function from unit to unit. So that's my new version of coffee break. And then I have this work routine, which is essentially something that produces some work. And so it's again asynchronous. So it has this type. It says, well, it gets a continuation that says, well, if the work is done, then give me the work, and it continues returning unit. So here's how I would have to organize that. It would have to say, okay, so let's do some work. And when that work is finished, I get the result in work one. Then let's do a coffee break. And when that's finished, well, that's just unit, so I can ignore the result. Then let's do some more work. And when that is finished, I get the result in work two. And finally, I call my continuation work done with essentially the two work items that I get here, which here are just combined with a plus for the sake of the demonstration. Okay. Good. So what we see here is that the order of the execution is essentially follows the indentation level. So where we would write a sequential execution, here the execution goes like this. So each new step is another sequence, so we get a lot of curly braces, and We get a lot of these essentially parameter things here. It's workable, but it's not exactly pretty. And we're not done yet. So the next thing we need to do is, what about failures? In typical programs, what we see here, that's essentially just the happy path where everything works as we intended. So what if the coffee machine breaks down or we get some other failure? So in synchronous programs, failures are handled with exceptions. So that's our first recourse to do this. So what happens if an asynchronous call fails? And we need to propagate the failure to the call site. Oops. So here we have this make coffee, which says, well, okay, we invoke the method coffee done, and the problem is we can't really raise an exception because what would happen if the make coffee thing, if make coffee here would do a throw, some no beans or whatever, it throws an exception. So would the continuation here be notified of that? No, of course not. I mean, if it throws, then it returns here. That's unit, that's the end of the world, right? So basically, whatever exception we throw here cannot be caught by anyone. It will immediately change, essentially finish the whole program. Once we write programs in this asynchronous style where essentially every follow-on computation is passed as an argument. So that doesn't work. So what we need to do instead is, instead of doing throw no beans, so that wouldn't work. So we have to cross that out. Instead of doing this, what we would have to say is essentially we invoke this coffee done here with essentially a failure no beans as the argument. So we have to pass the thing as an argument. And then by the same thing, we essentially, instead of a failure, if we actually do succeed, and we give it a success with some coffee. So failure and success together are in our try class that we have seen in the last semester. So try is coming back now. So try is essentially a way to to either encapsulate a value. So it's essentially its signature is try of plus t. It's a covariant class with a single type parameter. So in this case, we would have a try of coffee because that's the value of the success. Or in the failure case, that's the other subclass of try, then essentially we return an exception which tells us what has gone wrong. So to make these asynchronous programs handle failures, then it means that all the arguments that have to be tries so that we can pass on failure cases. So coffee done is now a function from try of coffee to unit. So that's essentially the situation that we're seeing here. So in the summary, what we have seen here is how to sequence asynchronous computations using callbacks. Callbacks introduce quite complex type signatures, as we've seen, and the continuation passing style is tedious to use. So a language that uses a lot of callbacks because it's used in the mobile space and essentially user interaction space is JavaScript. And there, essentially, this callback style is often called callback hell. So that you probably have learned that, have heard that term already. So callback hell. So that's what we've seen basically in this unit to say, well, if we want to do asynchronous, things get a lot more messy than synchronously, unfortunately. But it's sort of the price to pay for better resource utilization. Or is it? So what we do now after the break, I propose we do a 5-minute break, is a better way to organize these computations that makes them essentially better, more amenable to reasoning, that makes them easier to read and easier to write. And that will use a thing that is called futures. So that is the topic of our next mini unit that we do in 5 minutes. In the meantime, if you have questions on the chat, I'm on the chat, but we start again. Now it's 2:29, let's say 2:35. If you want to take a coffee break yourself, then please do so. Okay. Okay. What you can also do is, if you want to ask a question by voice, then you can use the raise hand feature, and I'm seeing that, and I'll unmute you so that we can talk if you want. So there was one question that I saw here in the chat at 2:22. K isn't volatile, so I guess they meant this. Let's see. Here, that variable K here. So one explanation here is essentially what we said is that the, let's see. So, right, so that method here, make two coffees, that for us is sequential. It's a single thread. So the idea is what happens in parallel is done essentially in make coffee. So the actual computation that computes a coffee, that essentially brews the coffee, that will be done in a different thread. So that computation has to essentially make sure that after it's done, it's properly synchronized and it's safely published and things like that. But for the moment, in this week, we're sort of above this level. We say that that's done in the low-level parallelism concurrency. We are essentially concerned with if we have these parallel computations that at some point invoke these continuations, how do we deal with that? How do we deal with synchronizing the continuations? But the synchronization itself happens in a single thread, so we're not concerned with volatile or not. It was a good question. Oh, we actually have one coffee enthusiast on the as a participant, so that's a good coincidence. Okay. So let's get back again. In the second unit of the course, we are talking about futures. So, and I should say that I forgot to mention that. So this is actually part of the reactive programming course, which is on edX and also the EPFL service. And the original author of the slides is Julien Richard Foy, who collaborated with several other people to essentially produce this course, Programming Reactive Systems. We'll see more contents of this course in the coming weeks when we talk about actors. So that's essentially after the Easter break, the new module will be actors. And since I'm at the course scheduling thing, let me also say that for the next week, we would have had the midterm, but as you know, midterms have been canceled. So what we will do is a mock midterm. So you find instructions on Moodle. The idea is that you should try to do the midterm exercises from, I believe it was last year's midterm yourself. And next week during the lecture slot, we will present solutions to the exercises. So I think that's probably a good preparation for the final exam, which we don't know yet when it will come, but it will come. So much is for sure. So what will happen is that the midterm is canceled and we will essentially scale the grades. So essentially we will proportionally weigh more the final exam and the projects, which are the other two components of the grading of this course. All right, but let's go back to futures. So what we've seen is that if we want to go from a synchronous program to an asynchronous one, then the types change like this. So instead of argument A, result B, we have argument A, continuation B, B to unit, and result unit. Let's massage this a little bit and see what we get. What if we could model an asynchronous, so essentially, so the problem with that approach is that we have these clumsy continuations that we see here. And what would be kind of nicer is to say if we could still return a program, have a program that goes from A to B, but now we wrap the B in another type constructor called a future of B. And that would somehow make it asynchronous. So that's essentially what we're after. So let's see how we can get there. So let's massage the type signature of our program a little bit. So that was this one here. So what we've learned in, I believe, week 2 of the first functional programming course is that we can essentially curry functions and that we can move parameters freely from the left to the right. So here we have something which is essentially does both steps in one go. So we have curried the thing, 2 parameter sections, and then we, instead of moving it to the left of the dot, we have moved it to the right of the dot. So we now say we have a program that takes an argument of type A, and it returns a function that takes a B to unit and gives us back a unit. So that's essentially this idea of currying. So in week 2, maybe it seemed academic and without much practical use for it, but now you see everything comes back and eventually will be useful. So we can do that, and let's see where that leads us. But before, I just want to make a quick excursion into mathematics, because it turns out that types and logical formulas are quite closely connected. And in particular, we have 2 things that hold. So one is that essentially instead of unit, let me just make this slightly larger. So instead of unit, unit is essentially analogous to false in this correspondence, and implication is function arrows is implication. So the arrow is the arrow. So let's look at this as a formula, now as a logical formula. So we say, well, it's B implies false, implies false. So what does it mean? Well, we know what implies means in mathematics. So it means so that's not B or false, right? And the whole thing is not this thing or false. Now we do Boolean simplification. So we have not B. So the not becomes essentially not B and not false or false. So not B is B, of course, and not false is true or false, and that is the same as B. So that's interesting. So that means that on this, if we treat it as a formula, our new program, this thing here, is actually quite the same as our previous program, which was written def program AAP, because B is really philosophically the same as B arrow unit arrow unit. Nice. So, and that's essentially a deep mathematical insight to look at this asynchronous style and continuation passing style. If you want to find out more about that, then we will have more about that to say in a course in the master called Foundations of Software, which essentially looks at this. Sorry, my software, which looks at this correspondence of mathematical proofs and programs in more details, among other things. So that's essentially was just sort of a little taste, to give you a little taste of the connections that you could see here and that are particularly prevalent in functional programming, because functional programming is closest to mathematics. Okay, good. So let's go on. So what we have as an intermediate result is now we've done that by a simple occurring and move things to the right. It's still the same program. So how do we continue with that? So that was the type signature we have. What we could do as a next step is we just introduce a type alias. So now it already looks essentially what we wanted to do. We say type future is T to unit. And if you look at essentially the variance, then you will find out that yes, essentially a T in this position, so twice inside enough left to the arrow, it's covariant. So we have a right to write a plus here. So it's a covariant T, and it's an alias that's defined as T arrow unit. And then we just write program A future of B. So it already looks what we wanted. It looks much nicer as a type signature, but we're not quite done yet, because we will essentially work on this future thing a little bit to make it essentially more feature rich. So what we do is we want to add failure handling as before. And now the advantage is, instead of having to put try everywhere in all the continuation arguments, we, at least in the type, we just put it in a single type as before. So we say a future now is really, it's not a function from T to unit. We have to deal with failures. So let's make it a try T. So either success returning it with a T value or a failure, and then it gives you unit to unit. Okay. So that's what we have. And now we want to embellish it a little bit. So that's why this slide is called Towards a Brighter Future. So how can we embellish it? So one thing we will do is we turn it into a trait, because then we can add more methods to it. So essentially, again, philosophically, a type like this, it's essentially the same as writing a trait, future of T, that extends this type. So it's a specialization of this type, and that essentially defines an apply method. The function here that you see here, so this function here, would actually have the same apply method. The apply method takes an argument of type trie of t to unit. That's precisely what we had here, right? And returns a unit. Okay, so now we have wrapped this thing up in a trait. The advantage of wrapping it up in a trait is that we will add further methods to it later on. So apply won't be the same, won't be the only method. But before we do that, we do a quick reality check and say, well, actually, it so happens that this apply is not called apply. So it's not called apply here. We call it onComplete because it's sort of more specific to tell you what it does. The apply is sort of just the generic thing to say, hey, this is a function. But if you look at future, you say, well, what does this function do? What does this apply of future do? And well, what it does is it says, well, a future is a computation, it runs. And when it's done, then it will invoke this continuation. So that's why it's called onComplete here, that we say on the completion, once the future is completed, that means it has produced a value of type t, then we continue with this continuation that takes a trie of t to unit. OnComplete, I should say, will be called when, like I mentioned, it produces a value of type t, or else it produces an exception. So it fails, in which case it will pass the exception to the continuation. So that's why the continuation is trie of t to unit. Good. So that's essentially the basic skeleton of a future, that trait here. So essentially that's the most important thing to understand about a future is that that's basically what it is. To define a future yourself, you have essentially to produce a trait, and you have to define its onComplete method, this one here. So essentially you have to fill this thing here in here. Okay, so let's put it to use. What we could do is now go back to our coffee break and now say make coffee. It no longer takes a callback, but it produces a future of coffee. So it will produce a coffee in the future. Okay, so what we do is we have a coffee break, which essentially runs this thing here. It says my eventually a coffee is make coffee. So what will this thing do? So it will launch make coffee, and it will start a parallel computation, start parallel computation that makes a coffee. And once the coffee is done, done, something happens with the future. So what happens with the future is once the coffee is done, the onComplete method of that future will be invoked, right? And so we have to do something with the future. So the way we use the future later on is we say eventually coffee dot onComplete. Once that's done, then essentially we have this try coffee here. It could fail, or it could succeed, and we say, well, try coffee for each drink. So the for each method in try will essentially run the drink on the coffee if it succeeds, and essentially just do nothing if it's an exception. Then we, of course, if there's an exception, we can't drink. So that's what for each does on the try. Okay, and then what we also do is we chat with colleagues. So what happens here? So let's just look at the sequence here. So make coffee launches the parallel computation and returns immediately. So we immediately go to this next thing, which says, well, onComplete, if eventually coffee is completed, then do this. That thing doesn't block either. That just says, okay, if this thing eventually completes, then go back to the thread and run this thing. So we essentially immediately go back to the next step. We can start immediately to chat with colleagues. And that's what we do for a while until the coffee break is up. And when the coffee is finished, then essentially the onComplete will happen asynchronously. Okay, good. So that's the thing with the futures here. So instead of the for each was a bit magical here. So we can also do this more explicitly. That we say the coffee break is really that we say make coffee, and then on complete of the make coffee, we pass a function, a partial function, a pattern matching function, I should say. So if it's a success, then we drink it. If it's a failure, then we handle the failure somehow. That's left out here. And we chat with colleagues. So that was essentially the meaning of the for each, is essentially that thing here, that if it's a success, then continue with the drink operation, and otherwise do nothing. That was the for each. Okay. Good. So what we did here was that we still haven't gained much. So let's see, compared to what we had previously, we avoid these callbacks to write and pass these callback arguments. That's good, but the basic structure is still the same. So the basic structure is still, we have to do these on complete talks calls here, and essentially it's still sort of we go deep. And the other thing that we noted is that we always have to deal with success and failure at the same time. So in each case, we have to say, well, if it's a success, then do this. If it's a failure, then do the other bit, which also can get tedious. So there are helper methods in failures which avoid doing it. Sorry, there are helper methods in futures which let us avoid doing that. And the helper methods are actually well known. You should know them by name by now. Clearly, so here they are. There's a map, there's a flat map, there's a zip, and then there are two others which are more specific to future: recover and recover with. So what does it mean to map a future? We'll get to that, but and same thing for flat map and zip. But why are they called map, flat map, and zip? So aren't they reserved for collections or databases or random numbers? No, actually, we can also use them for futures. And a good indication that they are the right names is that they have the right types for these names. So what was a map? A map was always something that essentially took a new type B and a function from A to B and would return you a new thing where thing was collection, or now it's future of that type. So map goes from A to B to future of B. And flat map goes from A to future of B to future of B. So that was exactly the same thing as before. We had that for trie, for collection, for arbitrary monads, we had map and flat map of these types. And since we see the same types here, it's a good guess to say that we want to make a map and a flat map. Before I get there, I just saw a question on the chat. What is the design reason of doing a case inside an on-complete instead of having an on-complete and on-error messages? None. There's essentially the two are analogous. You can do on-complete and on-error, or you can have a single method on-complete. In fact, I believe that the API, they give you both, so you can design it either way. Okay, good. So let's go back to this one. So let's look at map, flat map, and zip in a little bit more detail. So map. So what should map do? So map should transform a successful future of A into a future of B. How would it do that? Well, it would take the result of the future of A, pass it to the function f. So that gives us a B, and that would then be the result of the new future, which is a future of B. And what should happen if the future fails? So if the first future fails, then the whole result should be failure. So it should be also a failure of the resulting future of B. Okay, so here's a usage example of these futures. So we have a method grind beans, and that gives us in the future some ground coffee. And we have a method brew that takes ground coffee and gives us coffee. So to make a coffee now, what we could do is it returns a future of coffee, and it says, well, run grind beans, and when you're done, then map that so that essentially the ground coffee gets passed to brew, and that will give you essentially then the future of coffee. So it's a regular computation, but all in the future. So it's all a part of the future now. That's what we achieve with this map call here. Okay. So what about flat map? So flat map would have this signature here. So let's see whether the signature tells us something about what happens with, what should happen with it. So it would have to transform a successful future of A into a future of B, as usual, by applying a function f that goes from A to future of B after the future A has completed. So we complete the future of A. If we have a successful value, we run the f, which gives us a future of B, and that's what we return. And if the future of A fails, then we should essentially just return failure. And if that future of B fails, we should also propagate the failure. So we should propagate the failure in both cases. Okay, before we get to that, I wanted to make that a little bit more concrete and say, can we actually define map and flat map on future? So I give you a little bit idealized futures, but let's try that. So I'll share with a different thing now. Let's see that I get to that. Okay. Okay, so here we have on the left. Can everybody see that? Is it big enough for the code? Just yeah. Okay. Good. So here we have essentially our future trait written in the new Scala 3 syntax without curly braces. And what the future has that we know is it has an on-complete method. And now we want to add a map method. So what should we do for this? What should we do? How do we write map? Let's think about it. So what could we do with this future? So we have a future and we have a function, and well, essentially what we need to do is we need to produce a new future, right? So new future. There we go. So it's new future of B. And what should be in the future? Well, we have to define the on-complete method. So that would, okay, so for the moment, to make it simpler, I dropped the try. So I changed the on-complete method to be just A to unit. Let's forget about the error case for the moment. We'll get back to that. Okay, so what we want to do is we have to do on-complete, which now takes a B to unit, because we produce a future of B. And that returns over there. We have to define that. Okay, good. So what do we do for that? What can we do for that? Let's see. What do we have at our disposition? So eventually we have to call this on-complete here, right? That's the only thing we can do, that we say, well, to do the mapped on-complete, we have to call the original on-complete. So that would be self on-complete. And that takes a function from A to unit. So it takes an A. And what do we do with the A? So what can we do with the A? Well, we can call it F. So, okay. So that gives us a B. And now what can we do with the B? Well, we can call the K, right? The continuation. And that's it. So let's analyze that. So we say, well, our new future of B, it takes something that takes a B and goes to unit. That's my continuation. And what I do is essentially I produce a continuation that takes an A, transforms it with the F, and then invokes the key K, and then it passes it all on to self. So in a sense, we are sort of arguing backwards. We're starting. What you see here is essentially we in the end, the outermost thing is the previous one, the previous continuation, and we essentially build one that takes the program from one step further down from the B. So we sort of chain the continuations from the end of the program towards the beginning of the program. It takes some getting used to write that. But on the other hand, one good thing about type functional programming is in cases like this, the types actually guide you a lot. There's basically nothing else you could do given the types that you have. So that's essentially the meaning of map, what map would do. Let's try to do flat map as well, shall we? So again, let's say with this simplified version first. So we call it flat map. And the difference is flat map gives us a future and not a B. Okay. So now we have to write an on-complete as before, of course. And then, of course, we get a type error here, which says, well, we found a future of B, that's the f of A, and we need a B. The continuation gets a B. So what can we do? Well, what can we do with an f of A? We have a future. The only thing we can really basically do on a future, except for these now derived operations, is call on complete, right? So let's do that. Call on complete. What do we pass to the on complete? Well, that on complete is now a future of B. So it needs a continuation to B from B to unit. Where is it? Well, here it is. Here we have one handy. And that again gives us solves the whole thing. So that essentially is the only difference that between map and flat map, that we say a map calls the f on the previous result in the continuation and invokes k directly, whereas a flat map gets a future out of the f of A and then calls on complete with the continuation. All right, so let's do one more. Let's do one step closer to reality and make this thing a try of A. Now we have to deal with success and failure. So what would that look like? So we have let's see. So what we can do here is that we say, well, instead of getting the A, we essentially immediately pattern match on, sorry, that should be try of B now, right? Okay. So we still call self on complete, that the argument is a function that takes a try of A. So a good way to do this, we immediately match on success of some value A, or failure X exception. So that's our two cases that would match on this value here. Okay, so if we get a success, what do we do? Well, we call k of f of A. No, success of A. Right? So we say, okay, run f of A. That gives us a value, wrap it in a success, and pass that on to the continuation. And if we get a failure X, then we run k of failure X. And that's it. So that's essentially our new version that deals with both success and failure. Shall we do the same exercise here on the flat map? So we say, okay, one mic open, otherwise we wouldn't have a mute. Don't know, can some of the co-moderators see that everything is muted? Okay, so what we have here is we have the self on complete, and let's do the same thing. So success or failure. So if we have a success, then essentially we do the same thing. We do f of a success dot on complete. Okay. Wait, what happened? Now I have to see if we have a failure. So if we have a, let's see what it says. Okay, yeah, it's all right. So yeah, here we can't run the incomplete because f of a could also give us a success or a failure. So what we have to do is f of a. So if that's again a success of b, then we do b k of b. No, wait, f of a is a future. Right, on complete. Now we get it. It's a if we complete the future and it's another success, then we go with b, and if it's a failure, x, then essentially we go k of failure x. Why didn't this not? I know that's what we k gets. Ah, sorry, I'm completely okay. So it's a try b. So here it would be success of b. Okay, now we're getting there. Good. Okay, and now we're done. So that's basically what we have to do here. And again, you see you fiddle with it until basically the types work out and your program isn't too ugly. So, and then you have a fairly high chance that it works. But let's verify that anyway. So the logic to say, okay, so if the what the onComplete method for flat map would say, okay, run the onComplete of the left-hand side of the flat map. If we have a success, then map the function f of a, which gives us a future, and say run another onComplete of the future. So when that is done, we could have again a success, which is the thing that we pass on to our continuation. Or we could have a failure, that means this, the second continuation failed, which we pass on to our continuation. Or otherwise, the first future could already have failed, and in that case, we also pass it on to the continuation. Okay, so that is that. There you see essentially the fundamental way we can work with map and with flat map for these futures. And it's something that is quite surprising and gets some getting used to, that you say, basically here we have maps and flat maps, but there's absolutely no trace of a collection anywhere. So in previous years when I gave this unit, students came to me quite confused and say, well, how can you write map, flat map? There's no collection anywhere. People sort of got that an option is sort of a collection with between 0 and 1 values, and a try is sort of a collection of a success case and some exception, and a random number is in a sense a collection of all the numbers that are generated. But for a future is nothing. A future is something where essentially I have to argue backwards and thread the onComplete, the continuation threads. Which just shows that this example of monads, which have map and flat map, is much broader than what continuations are. I should also say, word of cautions, the way futures are defined here, namely that essentially they are, you can think of them as parallel continuations that goes on. It doesn't satisfy all the monad laws, it just fits into the monad types. So it's in a sense a weaker notion of monad, just like try is a weaker notion of sort of pseudo-monad, not quite monad. Okay. Good. So let's go back to the previous screen to the slides. So we've looked into details now of map and flat map, and we have seen not just how to use them, but also how ideally they are implemented. What's the way to implement them? So let's have a look at the third operation, which is also an old relative. We know it well. It's called zip. So zip is as its collection siblings, it takes two futures, a left argument and a right argument. And what it is, it joins, if they're both successful, then it joins the result values into into a single successful future of AB. Oops, that's a bit too broad. Let me just, okay. That's better. It joins them into a single future of a pair of values A and B. If any of the two future values have failed, it returns a failure. And it does not create a dependency between the two future values. So that's important. So that means if I write here, make coffees, and I zip that to make another coffee, and each of the make coffees is something that returns immediately and gives you some parallel computation, then what that means is essentially that none of the two make coffees has to wait on the others. So essentially, there's no dependency. You can essentially go ahead and make both of them and return both of them. So that's a much nicer way than what we had previously with this first coffee and the option. That the first example that you saw with asynchronous programming, which was really horrendous, how to make two coffees. So now you see with zip, it's actually a one-liner. It hides a lot of complexity that you see here. Okay, so how is zip implemented? So one way to think of it is to say, well, here's actually another way to make two coffees. I can use flatmap for that. Another way to make two coffees is this one here. I say make coffee, that gives me a future of coffee. So I run it with a flatmap, that gives me a coffee. And then I take that coffee and I make another coffee, gives me a future of coffee. I take that coffee and I return the two coffees. So the end result is again a future of coffee and coffee. But the question is that the same thing as the zip? Let's think about it a bit. What would you think? Is that the same thing? And the answer is no, not quite, because what happens here in the second one is actually we get a form of sequentiality. So the second coffee is initiated, that's the call here, it initiates making a coffee only once the first coffee is obtained, because that's a lambda, so that's a closure. So you run the closure only once you have the argument. So indeed, with these flat maps, it's strictly sequential. So we make the first coffee. Once we have the coffee, we start making the second coffee. It's not parallel as zip would be. Now the question is, can we achieve the same thing as the zip using the flat map? And the answer is yes, one can, but one has to work a little bit harder. So here's a way to do this. So essentially what we need to do is we have to pull out the make coffee from the flat map. So we say essentially make two coffees, run one after the other, that each of them gives me an eventually coffee one. So that means a future. So the types of these are future of coffee, right? So in the future, it will give me a coffee. I might have to wait for it. So these are the two futures. And by defining the two futures, I already run the computation. So now I have two computations running in parallel. And then I can combine them with the flat map. So I can say, okay, take the first future, flat map it so that once I have a coffee, take the result of the second future. Once I have a coffee, return the two coffees. So now it's again parallel because the actual computation happens here and here. So essentially the sequential nature of the flat map here is just essentially the final composition. Once I have two coffees, yeah, of course I I assemble them sequentially, but that doesn't cost me any time. Nobody has to wait for that. The flat map executes very quickly. So that also is essentially an explanation what the zip would do and how I could implement it. So basically a zip like this, I would have to, the internal implementation of the zip would resemble to something like this. So take the two futures and run them and then combine them with the flat map. Okay. So let's go back to our, now with the flat map and the map that we have, we can go back to our coffee break and let's see what that would look like now. So we have, as before, the work item, the work period and the coffee break. Both of them are futures, and our work routine now essentially says, well, do some work, flat map it with essentially the thing that takes the work, does a coffee break, flat maps it with it returns just units or underscore, do some more work, map it with work 2 and get work 1 plus work 2. Okay, so that is a reformulation of our coffee break using the map and the flat map, but of course it's still indented, right? So every step is one indentation level further. But now, of course, you probably have seen already what will happen next. So we have a thing with maps and flat maps. What do we do with that? Well, we convert it to a for, right? So that's basically what fors are for. So fors are things that map into maps and flat maps. So let's do the reverse mapping and map this thing back into a for. What would that look like? So here's what that would look like. So now our work routine is a future of work. And it's a for. It says, well, first, let's do some work. Name the result work 1. Let's do a coffee break. The result is uninteresting, it's of type unit. Let's do some more work, name the result work 2, and yield work 1 plus work 2. So now we have achieved essentially what we set out to do at the beginning, to say we want to have essentially asynchronous programming, but we want to essentially not have any nested calls or maps or flat maps in the logic that does it. We want to have essentially a straight line logic, a straight sequential logic, and we can do that by essentially what we did essentially was that we say we went from callbacks to futures. Then we added plus map and flat map. So that was essentially what our step that we essentially could organize futures, could combine futures better by adding map and flat map. And from that, then we went to for expressions. And that's essentially the thing that we get here. So I should say that's not academic. If you get a Scala job in industry, then I guess a lot of the Scala work does precisely that. So it is essentially about reactive server-side programming, asynchronous reactive programming, and it all comes down to either these fors in various frameworks. So frameworks are, for instance, CATS or Zio or Monix. There are a lot of frameworks out in industry that essentially all do that and then put it in some future or other. The future that you see here are a little bit specific in that they start immediately running when you essentially invoke a future. Whereas some of these frameworks, they are essentially more lazy. They were essentially the futures essentially just assemble a task, a computation task that gets stored in a graph or something like that. And then at the end, you push a button and you say, compute everything. That gives you a bit more control about the scheduling and things like that. But at a first approximation, it's basically all this. That's sort of what reactive programming is about. And I should also say that there's another notion of reactive programming that's based on different foundations, which are the actors, which we will see after the Easter break. But so essentially the world is a little bit divided into the future-based reactive programming, which is so futures. And the actors, there are also mixtures of the two. Basically, futures you need for almost everything, even in the actors, they're in a sense a more low-level thing. And the actors are start to really shine if you are going from concurrent to distributed. So distributed programming, where these computations can actually reside on different nodes. And you have to be failure tolerant, and you have to get replication and so on. Can be handled very well with actors, and cannot out of the box be handled by these things. So actors are essentially a more let's say scalable abstraction for distributed programming. On the other hand, they are essentially less functional and harder to use for simple concurrency. So for simple concurrency, I guess the jury is that you should use something like this, so futures or one of these frameworks. And once you go distributed, you should probably go consider actors. But in this course, you will see both. Okay, so that was the sequencing futures. So we saw we can write it all with a 4, which is nice. And another way to do our coffee break is here, that we say, okay, then if we have these parallel computations, so we have a future that is a make coffee followed by drink. That's my first future. And then we have our second future, which is chat with colleagues. And then we get here a future which says it's eventually drunk, sip, eventually chatted. So that would give us essentially a future if those is essentially if neither chatting nor drinking produces a useful result. So that would give us a future of unit and unit, which is not a very interesting type. It's two times the uninteresting value. So there's a final map here to say, well, let's just return a single unit instead. So that would be our idealized coffee break that we see here in this example. Okay, so I think it's good to take another 5-minute break because what we're going to do after the break is look at the other pair of methods that we still saw in future, which are the recovery methods, recover and recover with. So it's now 3:22, so let's say 3:27. We meet again for that, and then we go to the last unit. Okay, I'll also go and get a glass of water. So if you have questions, then please use the chat, and I'll get back to them once I had a drink. Thanks.
Onion. Valerie.
Okay. Okay. So let's see whether we had questions. Okay, for the mock midterm, does that include this lecture? I don't know. Is it? Well, you'll see. We will publish the questions of the mock midterm before. I'm not quite sure whether last year we did. I would guess probably not. Probably that was part of the final. Okay. Another question was, I don't see any appearances of threads or tasks or parallel. How are these computations performed in parallel? That's a very good question. The somewhat flippant answer would be to say, don't worry about it. They're performed by asynchronously on other computers. Somebody will perform them. But we'll get to that at the very end to say, well, if we want to do essentially these computations, then how do we perform them in parallel? There is a thing that essentially encapsulates called a promise, and it will be on essentially at the end of this lecture. We'll get to that. Okay, good. So let's go into the next unit. We're close to being done. We look at recover and recover with. So a task that we often have is that we essentially have a failed future. So something fails and then we try something else. So in the end, we want to have a success. We want to say, okay, we recovered from the failure. And we can do it by hand, of course. We can pattern match on the fail. And if we fail, then we can run a computation and return a success, which would then be essentially the recovery. But there are also helper methods that make it slightly simpler and nicer. So the two are called recover and recover with. So what recover does is it takes a partial function, so basically a pattern matching function from throwables, so from exceptions to result type B, and gives you back a future of B. And recover with is the same, except that the computations give you not a B, but a future of B. So recover is sort of the analog of map, and recover with is the analog of flat map. Okay, so a usage example is here that you say, okay, do the grind beans. And let's say we have no beans, so bean bucket's empty, that's an exception. What we can do is grind beans, recover with. If we have that exception, then refill the beans, which gives us, and flat map. Once that's done, grind beans again. So that would give us essentially grind beans gives us a future of coffee, of ground coffee, and so this recover with says, well, if that fails with the bean bucket empty, then refill the beans, followed by another grind beans. And once that's done, so this whole thing then is again a future of coffee powder, and that we can pipe into another flat map that takes the coffee powder and brews it. So essentially that's this recovery option. One small side thing, so these lower bounds, you probably saw them at some occasions already before, but it's still worth explaining that. So essentially future is a plus A, so it's a covariant method, so we couldn't, if we would write PF is a partial function from throwable to A and return a future of A, that would be incorrect because now we have an A in parameter position, which classifies it as contravariant. So our variance checker would say you can't define a plus here. What we need to do instead is we need to essentially declare this B with a lower bound A, and that makes the variance errors go away. And it also makes sense logically, fortunately, because what it means is basically, let's say you have the first future, it's a future of, let's say, string. And our recovery gives us back a list of int. So if the first future gives us a future of int, and if we recover, we get back a list of int. So what kind of future do we have at the end? And the answer is, well, we get the common supertype, so that would be a future of any ref. That makes sense because I mean either we have the original one that gives us a string, or we have the recovery that gives us a list of int. Any ref is the best we can get here, and that's indeed expressed by this upper bound, because we said basically we need to find the smallest supertype of A, which is string in this case, which also fits the result of B here, which also fits a list of int. Well, the smallest supertype of string that also fits a list of int is any ref. So that's the result that we're getting. So that's this trick with the lower bound. Okay. So we've seen the recover and recover with operations. Another thing that we have to handle is where are these continuations executed physically? How do we control that? And there are different options to that. So one would be to say, well, the continuation essentially happens on the same thread that calls it. And if you want something different, then you have to essentially do a fork yourself. Or you could use a fixed size thread pool for that, or you could be flexible, which is what the actual implementations of futures do. So what they do is they have, in fact, add an implicit parameter execution context to all the fundamental future operations. So that gets added to onComplete and map and flat map and everything. So the onComplete method then, essentially what it does is it says, well, if it completes, then it will invoke the continuation, and basically it will throw the continuation at a task, as a task into this execution context to be able to be run in the execution context. That's the choice of the existing future API. That's not essentially something that's fundamental to futures. That's just how the Scala 2.13 futures happen to be implemented. Like I said, there are other future frameworks like Monix or Zio that have different decisions here. But here in the futures that you have in 2.13, you could say that they are very, very parallel. Every essentially continuation bit is a separate task that gets thrown into the execution context and essentially gets picked up by the scheduler by something that executes it. Okay. So one thing to look at now is, let's say we have an operation make coffee, and that can essentially has two outcomes, which are we both pass as closures. So we tell it essentially to when you're done, it will take some time. If you're done, then call coffee done with the coffee that you've produced. And if you fail, then here's this on failure method that you have for both. And let's say we have that, and that operation that now there's no magic, no fork, it just executes. It's in the thread, it's defined in. So now the question that also came up in the chat is, well, how do I turn that into a future? How do I make that run in parallel? So I now want to make a coffee too. that returns a future of a coffee. And it should use make coffee because that's essentially my fundamental operations to make the coffee. So how do I make that into something that runs in parallel? And here's essentially what you do here. And that's what we essentially come to. That the first line is it builds a promise of coffee. And then it runs make coffee. So that's all on a single thread. So it runs the computation. Make coffee will take some time. And if it succeeds, then it will set the promise to say, well, I succeeded or I failed. So I just have to stop, show you these things in the API. Let's do this for a second. Okay, so here you see the docs of promise. So it's trade, and it has essentially two methods here. So it has the important thing is it has it can be turned into a future. So it can given a promise, we can return the future of that promise that gives you the future that wraps the possible results of the future that wraps the possible result of the closure into of the promise into a future. And then we have essentially two methods that essentially set the promise. So the first one is try success. So it says, well, my computation has finished, and here's the value that you should use return for the future. So if you call try success on this promise, then essentially the incomplete of the thing will be run. And the other is try failure. That's the same thing, just with a failure. So let me share now the other screen again. Yep, there we go. Okay, so that's what we had here. So here we create a promise, then we run make coffee, and that would essentially set the promise with success or failure, and we return this thing as a future. And that thing here, so that was actually, that's not in the slide, but that thing here can also be run as a fork. And probably if I want parallelism, I should run this as a fork or run a task run, yeah. Because essentially here we say, well, run this make coffee, and if the coffee is done, then we call try success on the promise, and that would call essentially p.future.onComplete. That would call the onComplete on the future that we return here. And failure would essentially call the onComplete again with the exception. So it would wrap the coffee in success, call onComplete, or wrap the failure in failure and call onComplete. So that's the idea how I can turn parallel computations, run with a fork of a thread, or run of a task, and turn them into futures. Good. So that's all we had. So as a summary, what you've seen in this video was that we have the future type that's an equivalent alternative to continuation passing. It's in a sense nicer to use, in particular that its map and flat map operations let you use for expressions for essentially asynchronous control flow. So you can, in a sense, pretend that things happen in steps one after the other, but in fact, everything happens asynchronously. It offers these convenient transformation and failure recovery methods. So transformation was map, flat map, and zip. That's the main ones. And failure recover was essentially recover and recover with. And the map and flat map operations introduce sequentiality, so sequential compositions of futures, one after the other, one after one result, you get the other. And zip gives you essentially parallel compositions that you run two computations together, and when they're both succeeded, then you return the result in a pair. Good, and that's all I had. So what you see in the backup slides, if you're interested, they're all up on GitLabs, is a previous version of the code course by Eric Meyer, which essentially gives you some additional material on the futures, but what we really need for the course is just what we have covered in this lecture. And that's all I had. So let's just see whether there are questions in the chat, or if you want to raise your hand. So let's see, what is the main difference between map and flat map? As always, it's in the types. We see, if we go back, let me just see where. Here we go. So let me show this. So what you see, the map operation, it's basically the type that we use to add to the future. So the map operation says transform the future with a function from A to B and return a future of B. So basically, once you have the previous one, run the function, return the future. And the flat map takes instead a function from A to future of B. So that means that now the second function, it also takes time. It can also suspend and will give you something later, and it returns a future of t. So that's essentially something that all maps and flat maps have. So a map is basically always, so if you have a monad of A, and then a map always maps that with a function from A to B to a monad of B. And a flat map is always the same, but here we have an A to monad of B. So it's always those two, that difference in type. And a flat map, if you remember it from lists, so that's where the flat came from. So if M is list, then basically a map produces essentially, given a list of A and a function from A to B, you get a list of B, whereas a flat map says given a list of A, sorry, that would be A, and a function from A to list of B, give you a list of B. So basically what it does, it concatenates all the lists, it flattens the list. And that's where the flat comes from. But it really, for the futures, it means basically the first one, you have a synchronous operation that transforms the future, and in the second one you have an asynchronous operation that gives you back a future, and you transform the future with that. Okay, cool, good. If there are no further questions, then I guess you have also deserved a bit longer break. So we start with the lab work at 4 as usual in the Discord or Zoom. I think it's all on. It starts all on Discord today. So I let you go and take a deep breath for 15 minutes before you start that. Thank you.